So hello everyone, good morning, good afternoon, or good evening, depending on your time zone. I'm Pascoal Pariuso, faculty member and currently the director of the Physics Institute at Campinas State University in Brazil, and also co-chair of the SCES 2020 conference. I'd like to welcome all of you to today's SCES webinar. Thank you very much for joining us for this event, and I hope you and your family are well and healthy during this difficult time. The SCES webinar series is organized by the chair of the SCES 2020. As you all know, SCES 2020 was postponed to next year due to the COVID-19 pandemic. So this series is organized to keep your community connected and live during the absence of the in-person SCES conference. So today the participants are welcome to ask questions after the talk. The participants in the Zoom meeting can ask questions using the raise hand feature, which can be found by clicking on the participants in the menu at the bottom of your screen. Then clicking on the small blue hand at the bottom of the participants list box. While the participants in the Facebook can use the chat to ask questions. So to improve our connection, I kindly ask to all the participants to keep the video off and muted during the talk. And then you can unmute yourself and start the video if you want to ask a question. So today, to introduce our speaker, I would like to invite Professor Anna de Visser from the University of Amsterdam. Professor Anna is a member of the International Advisory Committee for the SCES 2020. And also a co-chair of the SCES 2022 in Amsterdam. Professor Anna, thanks for being with us today, and you may begin the introduction.
Okay, Pascoal. So it's a great pleasure for me to introduce today's speaker, Dai Aoki. I think he's familiar to a lot of you because he's kind of famous in our field, I would say. So he's professor at Tohoku University. And a few words about his career. He started, he actually started in Osaka University. He did a PhD in the year 2000. Then for a postdoc, he went abroad to France, to Grenoble at the CEA. So he stayed there a couple of years. And then he went back to Japan and he became assistant professor at Tohoku University. He stayed there till about 2007. And then apparently France was so attractive again, so he went back to Grenoble, to the CEA, and he was researcher there for many years. But in the end, Tohoku was more attractive, and he went back to Japan, and he's now full professor since 2012. So he had a few, nice prizes. I think one of them is the UPAP Young Scientist Prize in 2008. And he was also awarded in 2010 a prestigious ERC starting grant from the European Community. So Dai is very well known for his work on 5F electron systems, so on actinides, so superconductivity and magnetism in these materials, in particular on in uranium compounds. And he is one of the, he was involved in the discovery of the superconductivity in uranium, rhodium, germanium back in 2001. He also discovered the first neptunium-based superconductor, and in 2009 he discovered a field reentrant or field reinforced superconductivity in uranium, cobalt, germanium. So he's deeply involved in these materials. He grows single crystals. He does many experiments with his collaborators, and now he recently started working on this uranium ditelluride. And most of you will know it is a kind of spectacular superconductor with field-boosted superconductivity and multiple superconducting phases. We had a short presentation about this last month by Priscilla Rose. Dai is now actually prepared to give us the full story. So Dai, please, the Zoom floor is yours.
Well, thank you very much, Anne. Thank you very much for your kind introduction. So I really appreciate. So now I just I will share my slide. Wait a minute. And you can see my slide. I think so. Yeah. Today, I'm going to talk about the uranium ditelluride. focusing on the reentrant superconductivity and multiple superconducting phases in phases. So, well, in fact, now it's 10 o'clock in Japan in the evening, so I'm a bit sleepy, and so, but I try to do my best for this talk. And yeah, so thank you for joining this webinar, and I tried to, yeah, I think it's a very interesting material, and I hope you get the interest of this material. So well, my affiliation is IMR Tohoku University, and also time to time, so I go to CEA-Grenoble, and so the financial support is here from JSPS and also JPhysics and ERC, and because this material is very related to the ferromagnetic superconductor. So if you have interest, so please read this paper, so which appeared recently. So this in this study, so of course we have I had a lot of collaborators, especially so in France. So my collaborator in France is Georg Knebel, Alexander Poulet, Jean-Pascal Brison, and Daniel Braithwaite, and Kunyu, and Michel Bariska, and Jacques Fouquet, and also Tohoku University, and well, here is Japanese team, and also CNRS in France. And yeah, so there are many people. And yeah, especially, so today I'm going to talk about reentrant superconductivity. So the reentrant superconductivity was measured in LCME Grenoble, and we measured with Georg and also Ilya Shakin. So before going to the uranium diterite, I want to start with the periodic table. Maybe you have not, maybe you are not so familiar with the uranium compound. So the uranium is here in the periodic table. So the 5f electron plays an important role for magnetism and so on. So here, this is so-called Wigner-Zeitz radius of metal. And so the uranium, the horizontal axis is the number of electrons, and 5f electron, so here it's drawn. And so this is a 4f electron system, so lanthanide. So this is well known as the localized 4f localized system, and there you can see there is a lanthanoid reduction. And on the other hand, d electron system, for example, so 5d electron system, so you can see large decrease of the Wigner-Zeitz radius. So this indicates the itinerant character. And so if you look at the 5f electron, the behavior is intermediate between localized and itinerant. So we can say that the 5f electron basically, so it has a dual nature between itinerant and localized. And of course, because of the 5f electrons, so there is a strong spin-orbit coupling, and the physical property is, there are a variety of physical property is known. So one of the example is the superconductivity. So here, so is a list of the uranium-based heavy fermion superconductor. So the first discovery was uranium beryllium-13 in 1983. Then, so you can see many materials known was discovered as a heavy fermion superconductor. And so the light blue color shows the spin-triplet case. So you can realize that there are many materials which can show, which has a spin-triplet superconductivity. I think it's quite rare. So spin-triplet state is quite rare, but in the case of uranium compound, there are many. In particular, so the ferromagnetic superconductor, uranium germanium 2, uranium rhodium germanium, and uranium cobalt germanium. So these shows the coexistence of ferromagnetism and superconductivity. So I will show you later more detail. And for this heavy fermion system, so the important point is correlation with magnetism. So this I show you some schematic view to show the relation between magnetism and superconductivity. So this is research area and this is the year. So you can see here the magnetism is known from long time ago. And the superconductivity is discovered so 1911. And at the beginning, magnetism and superconductivity believed to be a competitive phenomena, and these are antagonistic. However, so after the first discovery of heavy fermion system, namely cerium copper to silicon 2, so a new region appears. This we can call unconventional superconductivity. So this is year by year, so there are many materials discovered as which belongs to the unconventional superconductivity. So the schematic, the basic idea is, well, schematic view again. So here this region is magnetism, and this region is superconductivity, and here it shows unconventional superconductivity. But nowadays there are another axis. So this is, I would say, topological science. And so this region, so is exactly at our material. So, well, here is topological spin-triplet superconductivity is located here, and ferromagnetic superconductivity is spin-triplet superconductor, and also uranium ditelluride is also a strong candidate for spin-triplet superconductor. So it's located here. So the uranium compound is really a good playground to study the topological topological superconductivity, and to study this region. Uranium compound is a good material, good target. So in the ferromagnetic superconductivity, so there are many interesting phenomena, and one of the highlight is here. So namely the reentrant superconductivity in the ferromagnetic superconductor. This is this shows three materials: uranium germanium 2, and uranium rhodium germanium, and uranium cobalt germanium. So you can see here this is the H versus T phase diagram. So you can see the phase superconducting phase appears here, and so uranium germanium 2 shows a very strange shape of HC2 curve, like S shape. And in uranium rhodium germanium, it shows a reentrant superconductivity here. And so you can see here at zero field, TC is only 0.25 Kelvin. However, if you apply the magnetic field, you can see here the TC is 0.4. So it indicates that the superconductivity is really enhanced under magnetic field. And uranium cobalt germanium. So these materials, in fact, it's first discovered by Ann Visser's group. So we studied this material also, and so we found this kind of field reinforced superconductivity, like S shape. So this unusual HC2 curve cannot be explained by the conventional spin singlet state, so that we can believe that the spin triplet state is realized with equal spin pairing. Because equal spin pairing, there are no Pauli limitation, so we can expect very large upper critical field. And for this reentrant superconductivity is strongly related to the ferromagnetism. So this graph shows the relation between the magnetism and reentrant superconductivity. Here you can see the H versus T. In the case of uranium, rhodium, germanium, the Curie temperature is suppressed under magnetic field when the field is applied along the hard axis, B axis. Then the Curie temperature is suppressed to 0. Then the reentrant superconductivity appears here. Again, in uranium core germanium also shows a similar behavior. So Curie temperature is suppressed, then the S-shaped field reinforced superconductivity is observed. So this shows that when the Curie temperature is suppressed, ferromagnetic instability is strongly enhanced. Ferromagnetic fluctuation is strongly enhanced. Then the reentrant superconductivity observed. So now I want to switch to the uranium ditelluride. So well, before going to the physics, I just want to show you the number of citations related to the ferromagnetic superconductivity and uranium ditelluride. So this is a number, and the increase of the number is related to the new material, the discovery of materials. Here is the discovery of uranium germanium 2, uranium rhodium germanium, and uranium cobalt germanium, and now we are uranium ditelluride. So so today, now I'm going to uranium ditelluride in physics. So the first this material is first discovered by Shen Lang in the NIST group, by Nick Butch group. So they show in their paper, they show this schematic figure. So this is temperature versus ordered moment or spin fluctuation. So uranium germanium 2, uranium rhodium germanium, and cobalt germanium is located here because they show the ferromagnetic order, ferromagnetic state. Then superconductivity appears. And the uranium ditelluride is believed to be at the verge of ferromagnetic order, but it doesn't show us ferromagnetism. So, but I want to say that now I'm going to say that it's not very simple in this material. So I want to say more detail in this material. So before going to the more detail, I want to show you the kind of history. So in fact, so I got the news in to the end of 2018 from the two Japanese who joined the workshop in Canada, and they immediately sent an email to me that the discovery of uranium ditelluride. Then so I was really shocked. And then so we started the crystal growth immediately by flux method and chemical vapor transport method. And my colleague, so Harima-san, also immediately calculates the band calculation, did the band calculation. And then the paper appeared. And then so we get this crystal. And then so we found, we really confirmed the superconductivity. This is grown by flux method. And then so we get higher quality single crystal grown by chemical vapor transport method. Then so we confirm the bulk superconductivity by specific heat and so on. And then so I went to France immediately, and then so we have a emergent the meeting immediately. So here you can see the photograph of the meeting. So you can see some people. So this is Georg Knebel, this is Jacques Fulke, and this is Miniev. Then so my target is, and this is Jean-Pascal Brison, and this is Gabriel. So my target is to make a strong collaboration, so between France and Japan, and to fight against the American team. So then so we submitted the JPSJ and so on. So it's something like this. But this is a short history, in fact. So there is a long history, in fact. So we already studied this material in 2006. This material was studied by our postdoc at that time, Shugo Ikeda, and you can see here the resistivity curve. This result is already published 2006, but at that time we didn't see any superconductivity, and we realized it is heavy fermion, but then so we forgot. But so now we looked again our data, and we saw that here. So you can see a very small drop of the resistivity. At that time, we thought it's not superconductivity, and there is some stupid mistake or some experimental error, whatever. But this was really superconductivity. This is unpublished data. So for us, it was really shocked. And so in France, so we have a very common phrase. So this is c'est la vie. So this is a life. So, well, for this reason, so I was really excited after about the discovery of this superconductivity of these materials. So in fact, this is a fever. So the paper appears Shenran and our paper, and then this is some of the part of the list. And so in fact, it's a kind of fighting. So Japan, French team, and American. But this is part, and nowadays, so we already have 40 papers, more than 40 papers appear since 2019. So you understand, it's really, we are very excited. So okay, so I go to the physics. So here you can see the basic property of rhenium ditelluride. Rhenium ditelluride is a heavy fermion system, but it's paramagnet. The gamma value is 120 millijoule, and the crystal structure is body-centered orthorhombic. So here you can see the crystal structure. So the space group is, because of the body-centered, space group is IMMM. So the lattice constant is like this, so it's C long. And the distance of rhenium atom, first nearest neighbor is here. This is 3.78 angstrom, so which is a bit larger than the Hill limit. So that we can expect the magnetic order naively, but in fact, it doesn't show the magnetic order. But if you dope with selenium, so it shows the ferromagnetic order. However, the crystal structure is different. This is PNMA. By the way, this is the same space group with uranium, rhodium, germanium, or uranium, cobalt, germanium. Well, anyway, so it's so from this, so we can naively think about that uranium ditelluride may locate it at the proximity of ferromagnetic order. And before going to the superconductivity, I want to show you the normal state or some basic property. This is a band structure calculated by Professor Harima. So you can see here, so here this is Fermi energy. The red dotted line is Fermi energy. So you can see here there is a small gap at the Fermi energy. So from this, and the band structure shows rather flat band appears in near the Fermi energy. So the band, so this is calculated by LDA. So LDA band calculation shows very flat band and Kondo semiconductor-like behavior, small gap and flat band. And after Harima-san's calculation, so the Professor Yanase and Dr. Ishizuka calculated more detail using the GGA plus U method. So U is a Coulomb repulsion. So increasing the Coulomb repulsion, the U, so the Fermi surface appearing like this. And when the U is very large, So there is cylindrical film surfaces are predicted. Then, so the magnetism. Here you can see the magnetic susceptibility and magnetization. So you can see here, so A, B, C axis, and A axis and B axis, C axis, all directions show the nice Curie-Weiss behavior at high temperature, and A axis is easy axis. So this is a inverse magnetic susceptibility. So you can see the nice linear relation. And however, so here, so if you extrapolate to here to this direction, so you can see the Weiss constant is negative for all direction. From this, so it can naively, so we can consider the antiferromagnetic correlation is rather strong. And another important point is the magnetic susceptibility along B-axis shows the broad maximum at 35 Kelvin. So this broad maximum suggestive of metamagnetic transition. By the way, so also the magnetization shows a rather large anisotropy. A-axis is easy axis, and C and B is hard axis. B-axis is hard axis, and the hardest axis shows the broad maximum in the magnetic susceptibility. So from this, so this broad maximum may indicate the possibility of metamagnetism. So this is the relation between the T chi max here and the metamagnetic transition field HM is plotted like this. So there are many materials follow this relation, and so from this, so we can expect if 35 Kelvin, so T chi max is 35 Kelvin, so we can expect HM is close maybe 35 Tesla. And indeed, so it shows it shows a very sharp metamagnetic transition. So this magnetization measurement was done in Atsushi Miyake, and but so also Shen Ran also showed this reported the same similar metamagnetic transition. So you can see here at 35 Tesla sharp metamagnetic transition, and it shows a hysteresis. So this is indeed first order transition. And this, so if you draw the phase diagram, so T chi max here is connected to the metamagnetic transition like this. And because this is a first order transition, this can terminate to the this can changes to the crossover. So this point, so we call the critical end point, and this line is crossover and connecting to the T chi max. And at this metamagnetic transition, so we have a sharp increase, sharp peak in the specific heat. Here, it shows a specific heat gamma scaled with normal zero field gamma value, or the effective mass. So from the A coefficient of resistivity, or the gamma value detected by the magnetization using the Maxwell relation. So you can see sharp peak, and this is important for the superconductivity. I will show you later. And then, sorry, this is sorry. Okay, so now I want to show you the superconductivity. And this is a resistivity curve for at zero field. So here you can see this resistivity curve shows a typical heavy fermion behavior, and at low temperature it shows a superconductivity, and this Tc is about 1.7 Kelvin. And in the normal state, it follows nicely the T-square behavior. And the specific heat shows a sharp jump at 1.7 Kelvin. So this shows yeah. And the important point is strong, large residual density of state appears in the at 0 Kelvin. And this large residual density of states is proposed as a half-gap superconductivity at the beginning. And this half-gap superconductivity means one of the spin is not gapped, but one of the spin is gapped like this. It's like a so-called A1 state. But I should know, we should think about we should be careful about this possibility, because it's, according to Professor Miniev, second order transition from paramagnetic state to the non-unitary superconducting state is forbidden in this case. And also at low temperature, so temperature dependence indicates a point node gap in the along A-axis. So coming back to the ferromagnetic superconductor, so you can see we learned already. So the residual density of states is related to the ordered moment. Here is 1 μb, 0.4, and 0.05 μb. And there is the good relation with residual density of state and ordered moment. But so uranium ditelluride, it's paramagnet. So we can expect 0 residual density of states. So the question is why there is such a large residual density of state appears in this material. So of course, this residual density of states is related to the sample quality. So we measured different samples like this and plot like this. So this relation is already known in the high TC cuprate long time ago. And but so we don't know yet. So we have no conclusion so far at this point. And the similar results is also known by Andrew Huxley's group. And so in Grenoble, Curry-Paulsen measures the magnetization, low temperature magnetization. So here you can see the nice magnetization curve. And what is important is uranium ditelluride has HC1, lower critical field. And this is about 20 L state. So this is quite contrast to the case of uranium cobalt germanium. In uranium cobalt germanium, because this is a ferromagnetic superconductor and it's always in the mixed state, there is no HC1. However, in uranium ditelluride, we could clearly see the HC1. Okay, so now I want to show you the results of Nmr data. So this is measured by Professor Ishida's group in Kyoto University. Night shift shows a small decrease below TC. And this small decrease is, this shows a decrease, but it doesn't go to 0. So you can see here the scale. So compared to the spin susceptibility, the decrease is quite small. So this is much smaller than expected in the case of a spin triplet, a spin singlet case. So it's a strong indication for the spin triplet state. Another interesting point is this is not our data, but the STM data shows a chiral in-gap state detected by the group of America. So and also the Kerr effect shows a non-zero Kerr effect is detected by and so here you can see from this, so they conclude that the time reversal symmetry is broken. And also they show the specific heat curve. So this shows the double transition. This double transition is also reported by Los Alamos group. So I think previous webinar in SCES, so she shows double transition, I guess. And but this double transition is not confirmed by our group or Andrew Huxley's group or RAN. So this is still an open question. Okay, so now I want to go to the reentrant superconductivity. So here, so we measure the magnet resistance along B-axis. B-axis is a hard magnetization axis. So you can see clearly the reentrant superconductivity. Well, for example, 0.2 Kelvin, lowest temperature, the resistivity, magnet resistance is always 0 up to 35 Tesla. However, increasing the temperature, so you can see, for example, 0.6 Kelvin, so you can see it shows normal state. Then again, it shows a superconductivity here. So at high field, it really shows a reentrant superconductivity. And then, so 35, this jump shows metamagnetic transition. And here is more higher, the measurement up to 50 Tesla. So from this, so we draw the phase diagram. So this is a phase diagram, HC2 curve for A, B, C axis. So you can see here, A and C axis is 7 and 11 Tesla. So but the TC is 1.4. Well, depending on the definition, but it's about here. And for B axis, it shows a very strange behavior. So it's like reentrant behavior, field reinforced superconductivity. Then, so at metamagnetic transition, superconductivity is immediately collapsed, suppressed. Then it becomes normal state. So from TC, so Pauli limiting field is only 3 Tesla. So the all direction highly exceed the Pauli limit. So it indicates also the spin triplet state. And from this strange B-axis HC2 curve, so the many theorists also have interest, and Professor Machida or Yanase and Shishido, so they predict, they propose several other parameters like this, but these are different each other. So I think it's still an open question. So another important, interesting point is this result is first reported by Shen Rang. So this is H versus field angle. This is the B-axis, hard axis. When we apply the B-axis, we observe the reentrant superconductivity in this region. And metamagnetic transition, spin polarized phase, there is no superconductivity. But if you rotate from B-axis to the C-axis, this means that the hard axis to the hard axis, the superconductivity appears again at around 30 degrees. So this is really mysterious. It shows superconductivity in the polarized phase. So and this reentrant superconductivity is also confirmed by William Knafo in Toulouse. So this is real. So of course we have to the measurement was done by the resistivity curve. So we should confirm by the bulk, but at least in the resistivity this is confirmed. This is really mysterious. Okay, so the kind of summary I want to compare with ferromagnetic superconductor. So you can see the uranium, rhodium, germanium, cobalt, germanium shows the reentrant superconductivity or field reinforced superconductivity like this. And uranium ditelluride also shows a field reinforced, field reentrant superconductivity like this. But different point is in ferromagnetic superconductor, there is T Curie, and the collapse of T Curie induced the reentrant superconductivity like this. But in the case of uranium ditelluride, there is no Curie temperature. So the T chi max, instead of T Curie, there is T chi max. This is the the crossover, broad anomaly of the susceptibility. So this is connecting to the first order transition of HM. And then so HM, so above up to HM superconductivity appears like this. Okay, so now I want to show you the pressure study. So the pressure study is also very interesting in this material. So this is a phase diagram, temperature TP phase diagram. So here you can see at ambient pressure, it's 1.6 Kelvin. And then applying the pressure, first TC is decreased, then so it's split at 0.25 gigapascal. There is two transitions, and this two transition is measured by specific heat, AC calorimetry. Basically, it's thermodynamic response. So this is bulk property. So you can see here at 0.45 or 0.3 gigapascal, for example, you can see already the double transition, and 0.47, it's rather clear. And then, so above 1.5 GPa, it shows the magnetic, the superconductivity is suppressed. Then the another ordered state appears, and this is probably magnetic ordered state. And this kind of multiple superconducting phase is known, well known in UPT3, for example. Here you can see the H versus T, so there are ABC phases, and also uranium beryllium-13 doped with thorium. So you can see it, so the multiple phases. And of course, so we also know that the superfluid helium-3 shows multiple superfluid state like this. So this multiple superconducting phase is a strong indication for the spin-triplet state. So so our interest is applying the magnetic field. So what happened? So along B-axis, this is hard axis, we have a HM, metamagnetic transition. Applying the pressure, so HM is suppressing gradually like this. And then finally, it collapses at 1.5 GPa, above 1.4 GPa. And so reentrant superconductivity is smeared suppressing like this. But you can see here at critical pressure, so the initial slope of HC2 is very large. So it indicates that at the critical pressure, fluctuation is very strongly enhanced. And also here, so we had a critical endpoint at HM, and the critical endpoint is also decreasing like this. And then the fluctuation is induced. Okay, so now I go to the C-axis. So this is again the hard axis. So C-axis at the beginning, the HC2 is about 9 Tesla or 7 Tesla. So applying the pressure, so you can see the slope of HC2 is getting bigger and bigger. And at 1.34 GPa, it is almost vertical. And so this indicates that also indicates that fluctuation is very strong at the critical pressure. And Shen Ran's group, so they showed the schema, this kind of phase diagram. So in their paper, so although the field direction is not clear, but I expect that for C-axis, applying the magnetic field, and just above the critical pressure, there is a real field-induced superconductivity. I mean, at zero field, there is no superconductivity, but under magnetic field, it shows a superconductivity. This is a very strange case. Okay, so now I want to show you the A-axis, the results of A-axis. This is the easy axis. So you may think it's not so interesting, but indeed, in fact, it's very interesting case. So A-axis at ambient pressure is like this, but applying the pressure, so by resistivity curve, so we found this kind of unusual HC2 curve, the bump. So, and from this curve, so you may think about the possibility of FFLO like this, but it is not the case. So for example, ion selenide FFLO state, so is reported by Kasahara. So you can see here that they claim this is FFLO state, and this increase is very small in the case of FFLO. But here in uranium ditelluride, so it's very large increase. This cannot be explained by the simple FFLO. And so we measured AC calorimetry to study more detail in the inside of superconductivity. Here you can see one of the example at 0.7 GPa. This is a temperature scan. So we have a double transition measured by Daniel. So we confirmed, and then under magnetic field. And this is lower temperature part. Here you can see, and this is a field scan. So we detected several peaks, the anomaly like this. And from this peak, so we draw the phase diagram. So this is a summary of the phase diagram along A-axis. So you can see the phase diagram is quite rich. So the A-axis is like this, but applying the pressure, so you can see the 3 phases already at 1.4 GPa, and so HC2 curve, so detected by resistivity is this, and this enhancement, this enhancement is connecting to the lower TC. So this enhancement is due to the increase of this phase boundary, then connecting like this. And applying the pressure, it is the SC4 and SC3 is decoupled like this. Then finally, it's getting like this. And then, so at 1.7 GPa, so the superconductivity is suppressed, and then the magnetic ordered state appears. So we can say that this multiple superconducting phase indicates a spin-triplet state, but it's more not very simple. Not only by the equal spin pairing, it may be more complicated. And this or the strong Pauli-like behavior is observed. This is also interesting point, but we don't know what it is. And so and this multiple superconducting phase is also discussed by the theorist. So Professor Machida or Shishido and Ishizuka, so they propose this kind of phase diagram. So, but these are different each other. And at the last point, I want to say that the magnetic ordered state here. So the paper by Shenran and Nick Butch, so they propose this is a ferromagnetic order, and based on this schematic view. But so we can say this is not ferromagnetic state. So I believe it's not ferromagnetic state. So you can see the reason. Here, this is H versus T phase diagram for A, B, C axis above the critical pressure. So you can see the temperature, magnetic order temp Tm is decreasing with field or increasing like this, or vertical. So this phase diagram cannot be explained by the ferromagnetism. So rather than the ferromagnetism, I believe it's like close to the antiferromagnetism, or at least it's not simple ferromagnetism. And of course, so the ferromagnetic fluctuation is experimentally detected by at ambient pressure, it is detected by μSR, and also NMR, so by Tokunaga-san, so he shows the longitudinal fluctuation. And this indicates the ferromagnetic fluctuation is rather strong, at least at ambient pressure. And again, at ambient pressure, but very recent results appeared in arXiv. This so they showed the inelastic neutron experiment results, and they show the incommensurate spin fluctuation. So these results are somehow controversial, but so I believe so both in this rhenium ditelluride, so both ferromagnetism and ferromagnetic fluctuation and antiferromagnetic fluctuation both are important for superconductivity, and these are tuned. These can be tuned by magnetic field direction or the pressure. And this is a summary of my talk. So I showed the results of superconductivity in rhenium ditelluride, and HC2 highly exceeds the Pauli limit for all direction. And first order metamagnetism appears observed at 35 Tesla, and field reentrant superconductivity is found like this, and multiple superconducting phase under pressure, so detected for A-axis like this. So okay, so I want to stop my talk. So thank you for your attention.
Thank you very much, Dai. This was
Anna, so let's ask all the audience to unmute themselves so we can give Dai a very nice round of applause, please.
Yes, that was what I wanted to ask. Okay.
Thank you very much.
Okay, thank you very much.
Go ahead.
Yes, for this very informative presentation, very interesting material, many great results. I think there will also be many questions still. Yeah. So the idea is that people go to the participants list and then raise their hand in the participant list, and then we can organize the question session like this. Mm-hmm. And then I see there's a question by Elio Koenig. So please unmute yourself and ask a question.
Hello, thank you. Beautiful talk. I have a quick question about night shift. I didn't understand.
Night shift, yeah.
So far, there is only night shift for powders, or is it also night shift direction dependent for a single crystal?
Oh, yeah, this is not powder. So you see here, this result is this is measured by using this single crystal and H parallel B. Of course, so the important target is to measure the different direction, and so this is now ongoing. And I'd like to stress that I'd like to say that there. So Ishida-san's result is shows well. So in the normal state, it shows a nice KK. He shows a nice KK plot. So we can really believe that this signal is really coming from the rhenium ditelluride. So according to the first paper by Rang, so their measurement was done by powder. So this is a different point.
I see, and we are waiting for other directions of field.
Yes. I think it's a very interesting point.
Thank you.
Okay, then there is a question by Daniel Achterberg.
Yeah.
Daniel. Daniel, unmute yourself.
Here. Yeah.
Okay, can you hear me now?
Yes.
Yeah, okay.
I can hear you.
Okay, that was a very nice talk. I really enjoyed it. I had a question about the phase you showed for the field along the A direction as a function of pressure. And then you have this interesting phase diagram at 0.7 GPa, which shows a whole variety of phases.
This
here, exactly.
This one here.
Yeah, and so the question I have is, if I look at this phase diagram at 0.7 GPa, in some sense, it could be some kind of mixture between what you see at 0.54 and at 1.0. And so my question is it possible that you do have some sample inhomogeneity in this case here, and you're at some crossover between these two types of phase diagrams, and you're seeing a mixture of both?
This is, well, so for me, it's, this is not due to the sample inhomogeneity. But, well, to be honest, I have no clear answer on this point. But so according to Professor Machida, so he proposed this kind of phase diagram. So you can see, so the A, B, C, D, well, it's quite 5 phases. So, and here, this part, but
Okay, thank you.
Okay, Montu, Saxena. Please ask your question.
Sure. Hi, Daniel. Hi, Dai. Fantastic.
Hello. Hi. Hello.
Fantastic talk. So my question is kind of related to the to Daniel's one a bit. So you showed us that you had a residual part of the heat capacity, and that kind of went away as the sample quality improved. And I was wondering, would that then is there any effect of that same sample quality on the TC as well as on HC2? My main question, and a slightly related one, is that once we apply pressure and you're going towards this phase transition, so you may have not necessarily a kind of a multi-phase sample, but we may have a kind of a mixed phases as a result of pressure, not structurally, but electronically. You may have a mixture of things. So I was wondering if any thoughts of that.
Yeah, well, so it's I think it's I don't know, it's in fact, so of course, so TC is dependent on the sample quality, and so of course the mixture of the phases can be possible, I guess, because this material is very sensitive to the pressure, and even so in the pressure cell there is some, of course we cannot avoid the small uniaxial stress, so it is possible to have some due to that pressure inhomogeneity, so we have such kind of mixture of the phases. But
that's all right. Thank you. It's clear.
Yeah.
We have to investigate that. Yeah, thank you.
Okay, there is a hand up from Piers Coleman. Piers.
Hello, Dai. What a beautiful talk.
Thank you.
The project is clearly evolving beautifully. My question is, you have this very anisotropic magnetic susceptibility. Have you attempted to fit that with a crystal field scenario, and what can you tell us about what kind of crystal field situation we may have here?
Sorry, we didn't analyze based on the crystal field effect. So that we just we just fit linear to see the curious behavior and to get the mu effective moment. And that's all. So, but well, of course, I think it's we should analyze based on the crystal field effect. And but so I have no answer on this point so far.
Okay, I mean, clearly it's strongly Ising-like in the C direction.
Yeah.
And that probably places quite a lot of constraints on the underlying crystal field behavior. It may be very difficult to explain that with a crystal with a Kramer's doublet, for example.
I see.
So I'm very interested, particularly in, for example, could there be, would it be closer to a singlet crystal field ground state, or do we think we might have non-Kramers doublet behavior here? These kinds of questions might be revealed by trying to fit the data a bit more closely.
I see. Yeah. Okay. Yeah. Thank you very much for your.
Thank you. Great talk. Anyway. Yeah. Thank you.
So.
Okay. Then Kamran Benia. Kamran.
Yes. Dai, it's a very impressive work. Very, very
Thank
impressive.
you.
So I have a question. You think this magnetic order is not ferromagnetic, is antiferromagnetic. So maybe you can say what is your argument? And then I had a simple question. Is the transition from superconductivity to this magnetic order a first order transition? Do you have any evidence for this? Or is it second order? Or do you have any comments about that?
Well, at least experimentally. So, sorry. So maybe I show you maybe it's easy to. Yeah. So here the TC is at least we have no evidence for the first order. I think it's second order, at least in the experimentally.
I was thinking about this vertical line between the magnetic order and superconductivity.
So here.
Yes.
This. So yes, I think. I think it's TC is in fact strongly immediately suppressed. So you mean that this line? Yeah, I think it's kind of first order. It seems. I guess. So maybe let me tell you about another point here, at ambient pressure. So as I said, from paramagnetic state to the non-unitary superconducting state is not allowed. Direct transition. Sorry? Yeah, so the direct transition from paramagnetic state to the non-unitary superconducting state is forbidden. So from the symmetry argument. So if this is a first order transition, it is possible, or there is a if there is a accidentally degenerate here, or there is a double transition, it is possible to have a non-unitary superconducting state here. So the lower pressure part is also important point.
Thank you very much.
Okay, thank you. There are still more questions. One by Yashar Komijani, please.
So hello, thank you for the nice talk. I have a question on the initial data that you showed. There was this residual specific heat that was interpreted as a half gap superconductor. So what is the modern take on the residual specific heat? Does it still exist in the new samples, or does it disappear?
Well, so the point is, wait a minute. So maybe the point is, of course, the residual density of state is really depending on the sample quality. So if the quality of the sample is not very good, so we have a residual term. So the question is, for the best quality sample, for the ideal sample, so if we get the zero residual density of state or not, this is an important question. Yeah, and this is related to if it is if the ordered state is like A1 state or not. Right. So this is that's why. So it's an important question, I guess.
Yes. So, but you just rephrased my question. So, what is the answer? So, if you improve the quality of the sample, does the residual density of state go to zero or not?
No. Our best sample shows about 40% residual. This is 40%. And also Andrew Huxley's group also shows the residual density of states about 30%, I guess. So but so far we have no zero density of state.
Thank you.
I think.
Thank you very much.
Okay, the next question, Dai, by one of your competitors in the United States, Priscilla.
Very nice.
Hi, Dai. Thank you for
Hello.
First, I have to make a statement, and this is maybe a philosophical point, that I don't think that looking at each other as a competitor, a fierce competitor, is helpful. It can be actually harmful for the early career scientists in the field. We're all trying to do science here, right? And I think it's important to remember that.
Okay.
My point was following up on Pierce's comment, actually. And by the end of my talk, we had a brief discussion about this. You're absolutely right, Pierce. The ground state seems to be a singlet. So it's not a Krummer's doublet, right? So actually, in fact, I tried to do crystal field fits to the magnetic susceptibility. And you have a ground state singlet, which is separated by about 40 Kelvin for this, from the second excited state. And you may, that may remind you of uranium, ruthenium 2, silicon 2, right? So my comment is a very general comment that we need to understand the crystal field levels in the system. I think very little is known, right?
Okay, yeah. Okay, yeah, thank you for your comment. And yeah.
Okay, I see that there is also a question in the chat from Warren Pickett. So Warren, can you ask your question? If you unmute yourself. Doesn't seem to happen. If not, we could just proceed with Yakov.
Okay, nice talk. Actually, I have a very quick and simple question. How strong anisotropy in this uranium tellurium 2 from point of view of, let's say, resistivity anisotropy along the B direction and perpendicular in the perpendicular direction?
The anisotropy of the resistivity. So
yeah, for instance.
For this is in fact it's the important point somehow, because it's the important question is the film surface of this material. So theoretically, so if the U is large, so the quite very strong two-dimensional film surfaces are predicted like this here. But depending on U, it's more three-dimensional. And for this reason, so we had interest to measure the resistivity for J parallel A and J parallel C. And so maybe, sorry, I can show you the results for the, but it's not, the resistivity is not very anisotropic. So along between B and between A and C axis. Wait a minute. So the yes. So here this is J parallel C and this is J parallel A. So you can see the only twice bigger in C axis compared to A axis. So if it is two-dimensional film surfaces, so we can expect order magnitude difference between C and A, but it's not so. So it's yeah, this is the answer.
Yeah, this is actually a partial answer, but in some sense, intense magnetic field can also affect the interlayer coupling. Can you consider that?
Under magnetic field?
Yeah.
Yeah, I think, yeah, but yeah, well, at least the magnetic resistance does not show the strong dependence.
Okay.
So, as a function of field.
Okay.
Yeah.
Okay, I got it. Thank you.
Okay, then there is maybe a last question I see by Adrien Gourgaud.
Oh, Adrien.
Yeah.
Yes.
So, hello, Dai.
Hello, Adrien.
Yeah, thank you for this very nice talk. My question is kind of maybe a naive one in the sense that, I mean, the uranium-tellurium-2 seems to be like a paramagnetic kind of Ising-like material, right?
Yes, yeah.
And what I'm wondering is why would such a material that is not magnetically ordered would show a metamagnetic transition along a hard axis like uranium, rhodium, germanium would, and not a pseudo-metamagnetic transition along the easy axis, like for instance, cerium, ruthenium to silicon-2.
Yeah, so the reason why it doesn't show the magnetic order is in theoretically it is explained. So I think it's a paper by Xu. So the crystal structure is somehow special, and then so they discuss the somehow frustration occurs in this material. So because of the frustration, so they propose the magnetic order does not occur, but so both ferromagnetic fluctuation and antiferromagnetic fluctuations exist. So this is the theoretical view.
Okay, but shouldn't you be able to induce this ferromagnetic order by applying a field along the a-axis? I mean the easy axis.
Yeah, so it's not. I would say it's not a-axis, but the b-axis. So hard axis. So it's here. So you can see along b-axis. So this is somehow polarized phase.
Yeah.
In the polarized phase, so it's like it's like I'd say it's like a ordered state.
Yeah, like a reoriented state, like in uranium, rhodium, germanium.
And what is interesting is the reentrant superconductivity appears here. So you see here. So this is a metamagnetic transition, and this region is spin polarized phase. In the spin polarized phase, superconductivity reappears. So it's kind of there is some similarity to the ferromagnetic superconductivity, but well, we don't know yet. But this is also interesting point, I guess.
Okay, thank you.
Okay, I don't see any other questions in the participant list. Anyway, we had already quite a few interesting questions and discussions. So thank you very much for the questions. And I think we should thank Dai again. So maybe I should give the floor back to Pasquale to close the session.
Yeah, my sharing.
Perfect. Okay. Thank you very much for Dai for the excellent talk, and for Anna the visitor for helping me sharing the section. So before we finish, I would like to kindly ask all start your videos so I can have a very nice print of screen of this session of this SCEA webinar. Okay. Okay. Thank you very much, everybody. It was very nice seeing you all. Stay well, and I hope to see you next time. So bye-bye. Take care.
Thank you.
Bye. Thank you.
Bye.